Okay, everybody. Well, welcome to the very first webinar for the San Francisco Bay Area Council PELS chapter, the Power Electronics Society, where my name is Brian Zonstecker, and I'm the chair of the chapter here. But we are pleased to not only have our first webinar, but that also has enabled us to welcome a worldwide audience. So good morning, good evening, good afternoon, and all that to all of you. Thanks for joining. So not only I do want to congratulate you for participating in the first event, first webinar event for us, but you are also participating in the first event of the award-winning SF-BAC PELS chapter. That we have won the Outstanding Chapter Award for both our section, which is Santa Clara Valley, and the region, which is all of the western region of the U.S., and some other stuff which can't be disclosed at this time. But we started from nothing a year ago, and that's all made possible, especially by PELS members and supporting our events and getting the word out. So we appreciate that. So thank you all for letting us go in 1 year time from nothing until to the top chapter for IEEE. Just to let you know, if you're an IEEE member but not PELS, you can add PELS for free between now and August 15th with a code. Which I will put in the chat window right now. So you go onto the IEEE.org website, you log into your own account, and you add the PELS Society, and you keep going through the process, and you'll enter this code, and that'll should turn the $25 to zero, so you can be a free member. This webinar is being recorded, so the full webinar will be recorded with the the slides that are being shown exactly as you see it and hear it with the audio. As well as the Q&A, and that will be available on our website afterwards, as well as the speakers have generously decided to make their own actual slide deck also available. That'll be up there. So the format of this is we're going to have a presentation that's going to be on the order of about 45 to 50 minutes long, and then we're going to have Q&A at the end. So the Q&A, since everyone is on mute, the Q&A will be fielded by the moderator, me, at the end of the presentation solely via the chat window. So be sure and submit your questions via the chat feature in the WebEx window. Otherwise, we will not get it and not monitoring email during this and all that. I will read through them and feed the questions to the presenters, and they will answer in turn. And we will go through that as long as the presenters will tolerate or have scheduled for. I also like to note you can get professional development credit for this by completing a short form via a link that will be distributed after the talk. So with no further ado, I just wanted to introduce our two speakers today who will be speaking on the wide bandgap circuit optimization and performance comparison. And no, those are not typos. They are coming to us from the University of Cambridge in the UK, speaking the Queen's English. And so we are very proud to welcome Ed Shelton. He studied engineering at Cambridge University and graduated with a master's engineering degree in 1997. Since that time, he's worked as an engineering consultant developing high-tech products. More recently, Ed worked at Amantis, and he's now working at Cambridge University. Dr. Patrick Palmer attained his PhD from Imperial College London. In 1985, he was appointed the Electrical Engineering Division at Cambridge University. In 2010, Patrick founded Amantis, which has recently been acquired by MR. And so with that, I'm going to turn it over to Ed and Patrick. Welcome, guys. The floor is yours.
Thank you very much.
Yeah, thank you.
So I think I'm doing a lot of the talking, and then Ed's going to make sure I say the right things. So he'll kick me if I'm wrong. But hello, everybody, and I hope you enjoy our presentation. So I'll just move on from the beginning. You've seen this slide for long enough. There we go. Okay, that's good. So we've got a few things to talk about. We'll introduce wide bandgap devices, of course, but we want to talk about the GaN development platform. We like to think that that's our Ferrari of power electronics, and then we move on to the wide bandgap, the WBG development platform, which is much more down to earth and practical, perhaps. We'll explain the differences, and then we'll have a four-way showdown with GaN versus silicon carbide versus CoolMOS versus IGBT. This is not at this stage intended to be anything more than sort of interesting, a bit of fun, but hopefully we can learn some good things from that. And then, you know, some basic conclusions there. So let's just get underway. So let's go for it. Wide bandgap power transistors. What's the idea? Well, the intention with wide bandgap is thin devices essentially for high voltage, and that makes them inherently fast. You could do a Johnson factor for them, and then you learn that they should switch fast, and we all believe, I think, that they should be switched fast to get the maximum cost benefit out of them. And then that, of course, brings new challenges to us as power electronics engineers. We've met with various challenges, and some of the challenges are familiar. It's just everything has moved on, a whole new generation, as it were. And that's what we want to really try and dig at today. And often when people come to switch these devices for the first time, they'll get a lot of ringing, as you can see over here on the right. This is very typical sort of waveforms, lots of ringing. That's a bit of a disaster because you now have a very high peak voltage, which means your device utilization, if this is your steady state voltage, your device utilization becomes very poor, and you're just not getting value out of your devices with that ringing. Interestingly, we typically also see a lot of ringing in the current, and that's obviously related to ringing in the voltage, but this is because these devices also have more capacitance than perhaps we've been used to. So that's something else we're going to look at. And then ringing, of course, is always bad from the point of view of EMC, and increases dissipation in the devices too. So, of course, ultimately that can cause failure or early failure, reliability problems, which really we shouldn't be experiencing. What's it all about? Well, the inductances, of course. We know about inductances in switching from switching very high current devices. Now we're trying to switch perhaps smaller currents but very high speed, but in fact still we want to do high currents with things like automotive, electric vehicles and so on. So actually we're still looking at high current switching. We just want to make even more speed out of this thing. And common source inductance, of course, is the big no-no. We really mustn't have that. That's inductance shared between the gate drive and the power circuit. And that's a feedback inductance. And slow switching causes more losses, can cause failures from overvolting the gate. So that's a real no-no, and we need to really avoid that. Gate loop inductance is also important. We need to try and get that down so that the gate actually responds to the signals we give it. And here it's with these with any device, but particularly with wide bandgap devices mounted on a PCB, this is the area enclosed by the gate drive current path to the switching die and back again. We have to remember it's the loop around. It's the whole loop from the power supply through the gate drive back again. And then the one where probably, if you've got experience of power electronics, you're probably reasonably familiar with switched with the switch current commutation loop inductance. We put in freewheel diodes, we put in link capacitance, and we try and minimize that. I'll come back to that one anyway in a moment or two. All in all, we need to use here very careful PCB layout, and doing so, we got some results here on the right. We can get down to commutation loop inductances of nanohenries and a few nanohenries, and in fact on the GaN development platform, our Ferrari, we literally get down to half a nanohenry, just hundreds of picohenries. So it is possible to really push this down. So this is coming back to the, as I said, the familiar switch commutation loop inductance. We know how to build our circuits. We've got a half bridge leg here with our upper and lower devices. Very familiar TO247 plastic packages. Parasitic stray inductances. Stray inductances in these legs here. We put a capacitance in close, but you've got stray inductance internally in the capacitance. And then, of course, there's parasitic inductance to do with the circuit board layout as well. If you just did that on the top layer of perhaps a single layer circuit board, you could put all the components close together, but you've still got a reasonable amount of inductance. But we know how to do that sort of cheaply and effectively, and you know, with few problems. What we need to do when we're going faster is to really get that inductance down. And down here on the right, you can see that we can use surface mount power devices, very small ceramic capacitors, and a multi-layer PCB to get our inductance right down. Why is that? You know, what's the effect of this? Well, if we look at the switching, why do we need that capacitor at all? Well, when we switch, that we have inductance in our supply rails inevitably. We have inductance in the loads. It does, even if you say the load's a resistor. We switch so fast, any wire looks inductive. So we can just assume that all loads are inductors, and that's the fair assumption there. And then, just move that. We have two modes in our switch mode circuit. We have the on mode, if you like, when we've got the volts across the inductor. We're building up current through the bottom switch in this case. Here we've got the top switch just used as a diode for illustration. And then we turn it off. Well, that's fine. The current reverses, the current in the inductor stays in the same direction, of course, can't reverse, and is now flowing around a small loop here through this diode here. And you say, well, that's fine. But then you have to remember these inductors over here. They still need their current to flow. And that's what we've shown in this red path coming down through the capacitor. So that path through the capacitor becomes very important. And being able to, we don't mind this inductance here too much, as long as we don't have inductance in this path. Sorry, in this branch through here or through here. In other words, we've got to get this capacitor close to these two switching devices. Then it can act to decouple the inductances here. What does that mean in PCB construction? Well, we can do that. We're trying to minimize the loop inductance. So that means minimize the area of the inductive path around the board. And that's what we show in this lower diagram here. Using a multi-layer board, FR4, with flexi on top, in fact on top and bottom. So we've ended up with a 4-layer board with FR4 core. So this is reasonably standard assembly for a multi-layer board. But the difference here is we have heavy copper on the on flexi, and then we've tried to make this flexi thin so that our looped in inductance, if you like, through here is very small. And then we can arrange the capacitor here to be close to our switches. We've got a current sense resistor on the left as well. So the load comes in, here's the supplies either side, and we make a very tight loop around here. So that's reasonable assembly method. On the back of the PCB, of course, we can put things like measurement, well, the interfacing circuits, lots of other stuff go on the back there. We don't mind about that. It's getting this bit right is the critical factor, really. What's the impact on our circuit of this? Oops. Just get there we go. I think I skipped a slide accidentally. Okay. Well, what's the sort of impact? Well, let's put it the other way around. What's the benefits of putting all this effort in, changing what we do from what we've been doing? Okay, we want to go faster. We want to switch faster. We could talk about improvements for the circuit and smaller inductors and all sorts of good things, and I don't dispute they're good, but there is a fundamental benefit to be obtained from switching the devices better. So typically, when we've got a lot of looped inductance, high inductance, we have to moderate the speed at which we switch. We have a slow switch edge on voltage, and we end up, we have to do that, otherwise we end up with a high voltage overshoot. We still have to have a voltage overshoot because we've got to bring the current down. It's not shown on these diagrams, but we end up with a sort of compromise with a sort of slow voltage edge leading to a fairly big voltage overshoot to take the current down, and that ends up with a lot of losses, and we end up with a device that has to have a rating a lot higher than the DC bus rating. Well, if we do all this stuff with our surface mount devices and commutation loop low commutation loop inductance, what can we achieve? Well, we can switch much faster. So that gives us an immediate efficiency gain, shown in green, on every switching edge. So we can therefore switch to higher frequency. We're switching much faster, much lower losses. Therefore, as shown in the diagram, we can switch much faster. But even so, we've got much better efficiency. And then you get also what we call a power gain, because your overhead over your device rating or over your DC bus is much, much smaller. So you can use the devices much more closely to their rating if you can guarantee that the voltage doesn't overshoot much. So then you get a kind of efficiency gain and a power gain. And actually, if you think about it more, the power gain tends to give you another efficiency gain as well, in the sense of a lower voltage rated device typically has a better on state. Now, of course, there's limited range of devices, so you can't necessarily take advantage of that feature or factor, but it's there if you can take advantage of it. Okay, so let's look at conventional packages. My background is very much the high current devices, and 500 amp is not at all uncommon. And in that package, you've got about 100 nanohenries, so that gives you about 0.2 nanohenries per amp of switched current. The TO247, very popular device, 20 nanohenries, again, actually about 100 amps peak in that sort of device. So being charitable, you could say about 0.2 nanohenries there as well. Interestingly, if you look closely at that big IGBT module, you will see that there's some small terminals, and they've put in a gate return connection to that, and that's to keep the gate loop inductance well, no, that's to keep the source inductance, the common source inductance, small. The TO247 does not have that. Sometimes there's 4-wire versions of that available to avoid that common source inductance. Moving on, we can see that the surface mount packages, though, are a complete change of gear, and we're now down at very high currents, very low inductances, and inductance per amp is very small. And that means by package design, we should be able to get away with much lower overshoot voltages for normal switching. So if we switched the IGBT module at the 500 amps, we should expect about 100 volt overshoot, and that'd be very typical. Less with the TO247, but down with the surface mount device, we're down to about 2 volts. If we try to speed it up, of course, that's where we would get in trouble with the modules and the TO247, because then you're switching a much bigger DIDT, and you'd have much bigger overshoot voltages. But notice the surface mount device is an order of magnitude down in inductance, and therefore still very low overshoot. So we've got a real opportunity here to take advantage of the surface mount packaging and then the wide bandgap device with its speed inside. The two really need to go together, you could say. All right, let's move on to the GaN development platform. This is our Ferrari, and we'll just talk about what we did there to sort of build our Ferrari. Okay, so here, again, the same sort of idea with the multi-layer PCB in principle, but we took it a step further by pulling out some parts of it onto a very thin flexi PCB in this thing that looks like it's got wings. And we've got the capacitance banks out on those wings there. The other wings have the current measurement, and we've got the low inductance EPC devices here, 200 volt, 22 amp. So this is, we're not playing around here. It's a 22 amp device there. We need all that capacitance and so on to decouple even the low stray inductance that we've got on the PCB above. Okay, some other things we'll talk about this a little bit more in a moment. Other things we rationalized as well was that you cannot measure anything in there very easily. So we must integrate measurement circuits into our Ferrari here to know what's going on. So ultimately one might take those out, but at this stage we need to have them in so that we know what's happening, and we'll talk about that in a little bit. Another thing, of course, was gate drive, and we have our own way of doing gate drive, which we'll explain also. Okay. There's the sort of motherboard. That's in the previous slide, that's the conventional PCB, and there you can see the power subcircuit, as we called it, or daughter board, sitting in there on the motherboard. Lots of circuitry there to do, also some more capacitance decoupling, interfacing the measurements off to the oscilloscope, all takes op amps and all the rest of it. So all of that is pushed off onto the motherboard, and you know, it looks like a big circuit at one level, but the real switching is done in the power subcircuit. But why are we integrating in measurements? Well, because if you tried to do measurements, you would increase the inductances of the loops. You would be putting in terminals. It's getting, those of you who are involved with ASICs and design of semiconductor circuits and so on, you'll be familiar with the idea that measuring stuff is very difficult. So that's what's happening here. We've shrunk everything down, and therefore measuring becomes a difficult thing to do, and we have to build in the measurement circuits. That's just to give you a bit more scale. There's a picture of the die with its solder pads in there. So that's a kind of flip chip type of idea. And then you can just about see those chips, and compared to the size of the pen there, a normal pen. So this is a roughly a 100 volt, 20 amp circuit. So if you multiply those together, you're coming out with 2 kilowatts in a tiny little arrangement there. As I say, this is our Ferrari. What about our inductances? So we needed to do some measurements. So Smith charts, we can use the voltage network analyzer, and we can get Smith charts off it. With the current measurement in there, and all the devices mounted, we have a total commutation loop inductance of 750 picohenries at 600 megahertz. If we took out the current measurement, just put in links, we go down to 500 picohenries. So you can see the even integrating in measurement circuits, we do make a considerable, we do affect the circuit considerably in proportion, but we still consider this all very small. And then if we took off all the components and just had the one transistor, we can see that it goes down to 100 picohenries. So it's this idea of the flip chip is really very low inductance. The Flexi PCB is really working for us. Okay, well, we need to talk a little bit about gate drives, and a lot of people are very worried about GaN devices and how to switch them and gate and so on. Our feeling is that actually they have a limited voltage range on the gate, and that's something again we'll come back to. So our feeling is that actually you'll do well with the current source gate drive to get the control that you want through the switching process, noticing that the gate is a capacitive load. So that's what we built as a current source gate drive, 650 megahertz bandwidth, of course going into a capacitor, so it's sort of integrating, and a very, very small propagation delay. We were aiming for potentially closed loop feedback control, and we really wanted a very small delay there. As I say, small gate voltage range, +6 to -1. But we want to put in a lot of current in there, 400, ±400 milliamps. You could say, well, you know, it doesn't sound like the device is going to be safe in its on state and off state. Well, we overcame that by adding MOSFET clamps to the supply rails in either the on or the off. And I think also that's a good idea with these GaN devices. At the moment, that was all done discrete, but clearly that could all form a nice ASIC. Okay, let's think a bit more about some of the measurements. We've got to measure currents, voltages. We really need to somehow do all of that. So what we did was an RC potential divider for the voltage, and then that's buffered, as it says there, into 50 ohms to output into the scope. So that means that, you know, all the amplifier stuff is done on that motherboard, and that allows the measurements to not suffer from any kind of pickup or anything. It's going into a 50 ohm cable, and it's all terminated properly. So we're very confident with that. The current measurement, again, we can't use normal probes. They haven't got the bandwidth. They're too much insertion loss and performance degradation. So we built our own. So we used a resistive shunt, but you know, we're still at the very high switching frequency here. So even the surface mount resistors are going to have significant inductance. We just saw that. There's something like 100 nanohenries, 100 picohenries or so, and we're going to have to compensate or filter that in some way. And then that's amplified and buffered into the scope 50 ohms as well. And then similar things for the gate voltage and gate current. So here we have it switching. The diode in the circuit there, in fact, is a device that's is a GaN switch there, just with no gate drive, acting as a catch diode. And we're switching 100 volts, 10 amps under these conditions. We're doing a double pulse test to make sure we haven't got any power dissipate, well, to make sure we don't melt it with power dissipation. We just want to see the switching and how fast can we go. And that's connected, with, as I say, with all these 50 ohm connections to the LaCroix scope. We've got more detailed waveforms here. So it's a sort of middle gate drive. We get very nice switching. Well, I hope you think that's very nice switching. We like to think that those are kind of ideal waveforms, really, and they're 20 nanoseconds of division. No voltage overshoot there in the sort of pink, and there's a little di to T drop, and that's due to the device capacitances. So this is something we learn again here. We've got rid of inductances, we've got new wide bandgap devices, and suddenly we're meeting capacitances head on. At turn on, you can see this very clearly with this big overshoot current at turn on, but still very clean waveforms, no ringing at all. And we'll show in a moment that overshoot spike is simply due to the capacitances. But we're very pleased with those waveforms and show that these devices can be switched very cleanly, very quickly. So that's 100 volts in 10 nanoseconds. That's 10,000 volts per microsecond on these devices. And then the current is really cracking along at, what's that going to be, 2,500 amps per microsecond. Okay. Just to show that our gate drive does have control, we can, and also really to show that it's important to have control of your gate drive, we can see this capacitive overshoot bump with a slow switch on the left and a fast switch on the right. And it's off the screen in our experiment on the right. It's really fast and horrible in one way, but nonetheless the waveforms are still very clean with no ringing. Switch off, similarly you get a similar effect. You do have a capacitive effect, but the capacitive effect at switch off actually is very nice, and you can see that on the bottom right where we switch off very fast and the current's coming down very fast before the volts come up. So we get a kind of snubber effect for those of you who remember what snubbers are. And that's pretty cool because that reduces our losses. But of course we pick up the losses again at switch on. So we haven't really won anything there. The only win we get is by sheer speed. Let's just do a little rough calculation here. So our top device is a GaN power transistor with an output capacitance from the data sheet, 240 picofarads. The stray capacitance we measured off the voltage network analyzer, 20 picofarads. Put that together with the voltage, 100 volts we're switching. We need a charge of 2.6 times 10 to the minus 8 coulombs. We've got to put that charge into that capacitance. If we then compare that to the switched waveform on the bottom right, you can see that we can do a simple triangular shape, and we come out with almost exactly the same, 2.5 times 10 to the minus 8 coulombs. So we have entered the world of capacitances, really, in these devices, and we need to show that we can control the switching to avoid enormous current spikes there. Okay, so that was the sort of conclusion of that bit, where we're showing that very clean, very fast switching of GaN hemp devices is possible, and we've also shown that embedded measurement gives us real insight without terribly impacting the circuit at all. It was a Ferrari, so we had to build this low inductance current commutation loop, but then we get no voltage overshoot, so it's really very clean. We can show that our current source gate drive is working well at controlling VDT and DIGT, and we think somewhere in the future we may be able to profile the waveforms and use closed loop feedback control to make sure that we stay in a sweet spot in terms of switching. Don't forget, all of that technology is applicable to all the fast devices, and in fact that's what we'll be moving on to. So the wide bandgap development platform, the logic of this one was to try and build something that's much more sort of conventional design in terms of the layout of the components we're using. Also going up in voltage. One of the advantages of wide bandgap devices is high voltage parts. So we want to go up in voltage, accommodate various different devices and package outlines, take advantage of the surface mount DC bus capacitors. So take advantage of what we know about laying out the PCB circuit, and you can see on the right there, we've just laid these in a straight list, so it'd be easy to make this PCB. We've got the big bulk capacitances there in blue. We have the devices. In fact, you can see a TO247 up there as well. The black wire is our load connection. The inductance in that really doesn't matter. We lifted it out of the board because the capacitance, we added too much capacitance with that wire, and therefore we should have tracked it on the bottom of the board or done something different there, but we've taken it as a wire straight up the top. You know, we seem to, even though we know, we forget these capacitances and we can make mistakes. It's easily done. Again, we've got the current source gate drive with profiled control and embedded measurements for exactly the same reasons as before. Okay, so a little bit, you know, what do we mean by a current source gate drive? We sort of smeared over it before. And here's the, here it is. It really means, you know, you can't buy a current source. Why do you want to do it? Well, because the Miller plateau VG varies with all these different MOSFET type devices. The plateau varies with the current level, and therefore your switching varies with your load current. And okay, if you're in some applications with a very known fixed load current, it doesn't matter. But many applications, and particularly as we move up in volts, we start to look at motor drive applications and other sort of sinusoidal load current applications. So we've got a widely varying load current. Therefore, we would have very widely varying switching. So we really want to resolve that by eliminating the effect of the Miller plateau. So here we've got a current drive, which is pretty straightforward, op-amp with a 10 ohm resistor in the feedback loop. And that gives us that nice switching there. We can test that to find out what its bandwidth is. And as you can see, we've got simulations, we've got voltage network analyzer tests, and it's pushing up to about 200 megahertz bandwidth there. So we can do quite a lot of profiling the gate current if we want to. At this stage, we haven't done that. We're doing, well, we sort of do simple switching profiles. Current measurement, we mentioned this before, we use a sense resistor, but they have inductance, so we need to somehow compensate, filter that, and that's what we've shown in this. But then that's buffered out, but we're using differential mode amplifiers to try and get over some of the pickup. There's a lot of pickup, and we're going to meet that again later in a few moments. Okay, looking at the current measurement circuit, though, the network analyzer is showing very nice performance. The simulation shows good performance. The network analyzer shows good performance too, up to 200 megahertz. So not as high as we had before, but pretty good. Voltage measurement, pretty straightforward, but using capacitance, potential divider, as well as resistance to give us the wide bandwidth. And then we've got, the buffer op amp into our 50 ohm cable. So that's pretty straightforward. Measurements there, the bandwidth in this case, I haven't written it down. The bandwidth's about 200 megahertz again, so we're up in the right sort of place. We did check that one, by the way. That one is, voltage is something you can check, but I would say that you still, if you use an oscilloscope probe, you still run into problems with the earth clip and pickup from that little inductive loop you've got, little pickup loop between the scope probe and the earth of the scope probe. So you still will not measure as cleanly with an oscilloscope as you will with a built-in circuit. So it's very worth doing this sort of stuff. We talked about capacitances. Here's our double pulse switching as before. Interestingly, we took the load current down to nothing over on the right, and you can see that we switched nice and quickly, so 50 nanoseconds of division, so nice fast switching, and we get a nice pulse of current through our current measurement circuit. So that's the device, the bottom device, switching the capacitances at that top node, the other device, and you can see that that's a pretty significant capacitance, pretty significant current that you get from those device capacitances. Just to show actual waveforms on the scope, I always like to do this just to show that it's sort of kind of real here. And in fact, you can see the capacitances, the light blue traces on the bottom oscilloscopes. You can see the effect of the capacitance again in the sort of overshoot on the left, and turn on the cut, the drop in current. But again, notice very, very clean voltage switching waveform at turn off. Very clean waveforms throughout. Now this is looking at the downloaded versions, and you can in fact here we have put the scope probe on, and it's the scope probe in yellow on the voltage. So you can see that the scope probe is picking up a bit and ringing a bit. You'll notice there's a little bit of ringing on the current. I think that ringing probably is there in this case. In the later traces, I'm not always sure. Okay, thinking about did our gate drive work? Well, here's the DVDTs that turn on and turn off with low current, low load current, and high load current, and you can see that they're pretty much the same. We're effectively driving the Miller capacitances at this point, and they're very. The gate drive is a constant current, so we get a constant DVDT. Oh, just to say, low current was 9 amps, high current was 18 amps. So this is significant switching. Okay, well that's the sort of hard work. That was being in school for a bit, and I'm sorry about some of that. There's nothing we can do about it. We've got to explain that sort of thing. But we built this wide bandgap thing so that we could test different devices. And so we're going to move on to our four-way showdown. And we've met these capacitances before. Here's the classic capacitances of MOSFET. The interesting thing, in a four-way showdown, we are doing effectively three FET devices and then the IGBT. And people often say, well, surely the IGBT is a slow device. Well, actually, the IGBT can be as slow or as fast as you design it. And that will come out in a moment or two. But just from the point of view of capacitance, the IGBT also has a charged plasma of holes and electrons inside, and the consequence of that is that affects the switching. You're not simply driving capacitances, or not simply driving the capacitance from the circuit. You've got capacitances that are building up due to the currents and so on in a different manner. And that's worth bearing in mind, and will come out in a moment. Nonetheless, MOSFETs and IGBTs are, been around with us for a long time, and we can do a lot with them. So let's do our head-to-head comparison. Things you start to pick up here. I don't know if you can. I hope you can see the mouse here. The GaN devices, again, low sort of drive. Here it's a GaN systems device. Here it's sort of low drive requirements. Silicon carbide, very high drive requirement. That's due to the low mobility in the silicon carbide channels. And of course, you're making small area devices, so again, there's not so much channel in those devices anyway. So it's a kind of a bit of a problem for silicon carbide in a way, in that it comes from both directions. A smaller area device, and then so you've got less channel, and then the channel's not so good either. So that's a bit of a challenge. And then the super junction, we can really drive this thing hard. This is our classic MOSFET, and the IGBT, again, we can drive those hard, but we don't really have to, but we generally want to get the best on-state performance. This is an interesting one, this sort of idea of the transconductance. The GaN device is very high. We've had to estimate these from the data sheet, but the GaN device, very high transconductance. So you move the gate a little and you get a lot of current. That's what that means. In our switching situation, that means we need less gate voltage over threshold for a particular current than we would with perhaps silicon carbide. So notice this is 12, that's coming up very high. It's coming up very nicely with the silicon superjunction, and the silicon IGBT is really winning here. But that's because you're kind of getting this sort of extra gain, if you like, from the bipolar. I don't normally like to talk of it in those terms, but in this context, that's quite a useful way of looking at it. And the poor old silicon carbide MOSFET is struggling down here with a low transconductance. That means you've got to do a lot of work on your gate voltage to get up to your full current. Well, okay, it's I've criticized that, and you could say, well, actually, it's a lot smaller capacitance. The superjunction MOSFET has a huge input capacitance. There it goes. It's really big. The IGBT, very modest, actually, very similar, funnily enough, to the silicon carbide. And then the GaN device, really, or both GaN devices here. I haven't said much about this one because we didn't switch it, or we did switch it, but we didn't present it. These are low input capacitances, very nice indeed. And then our output capacitances we're also driving, as we talked about. These are pretty low. The IGBT really starts to lose out because of its stored charge. Reverse transfer capacitance, that's an interesting one. That's our Miller capacitance. Very variable in design here. Pretty small here, very small here. And then, of course, this is a large chip area here, and that's quite large. People often talk about charge, and here's the, sort of different charges here. Again, quite a lot of it in here and here, but very small here. These are the test conditions from the manufacturers, not ours, but just to try and compare similar devices, similar ratings on the data sheet here. This says 8 amps, but it's 8 amps under particular conditions, and it's a pretty similar looking device. Okay, let's go forward and okay, I might smooth over some of this, but what you notice is that the capacitances are all voltage dependent. Sorry, the input capacitances, the gate capacitance contribution of that isn't voltage dependent, but the output and reverse transfer or millicapacitance is. Notice different sort of magnitudes here. This drops right down. We've already talked about those magnitudes. This drops down very fast as well in a relatively low number of volts. Be careful, this is on a logarithmic scale. Same sort of thing here, rapid drop off on the superjunction in particular. Again, probably something to do with the superjunction design. Okay. Oops. So I picked out in just a couple of things in red, this very low reverse transfer capacitance, very low gate drain charge. So this really opens up the idea of fast switching, because we're really not having to put much current into that gate to get it to do everything. We talked about this gain, the transconductance up here. So let's go and do it. That's just to prove, that's me in the lab, just to prove I do this stuff, but notice I'm only driving the scope. I'm in the PC driving the scope. I am driving the scope through the PC, but I haven't got my hands on the hot end. Neither has anybody at this, of course. Very dangerous stuff. Anyway, there's the nice switching waveforms that we saw before. 400 volt, 10 amp. We're doing this with all the devices. We're using the same, to make things a fair test, we're using a silicon carbide freewheel diode in each case. So that's no difference there. So here we go with the GaN device, full-on gate drive, very fast switching here, no voltage overshoot to talk about. Little anomalies happening here in that we're driving this very hard, half an amp drive, so a little anomaly in the drain source voltage here. It's lifting up a bit early as the gate does something here, and then boom, it goes really fast. Notice the current is doing something slightly horrible in terms of ringing. We believe that's the op-amp circuit buffer just going off and ringing on its own. This is common in GaN switching, that the EMI is so high that it sets off other parts of the circuit. So we hope to improve on that in the future. Turn on, as I say, turn on very clean voltage here. The big current happening there, and then going into ringing. But 50,000 volts per microsecond, we're really going for it there. Dropping down the gate drive, the DVT is a bit slower. We've sort of calmed it down a little bit, but actually there's no real difference there. What we have done is we've got rid of some of these little anomalies here, and the thing's behaving very cleanly, and we could say that that's pretty optimal. Go to silicon carbide. We can put the whole sort of switching cycle on one screen here, and you can see very nice voltage waveforms, no overshoot again. Pretty nice current waveforms. We saw this sort of ringing, a little bit of ringing before, so that's the same sort of ringing again we're getting. We can see the ringing in the gate voltage, so we believe this is real ringing with the capacitance of the devices, but not huge. Very nice waveforms there, about 32,000 volts per microsecond, so still very fast that turn off. A bit slower, well, considerably slower turn on there. And then if we drop the gate drive down, you can start to see in fact, you can start to see the effect of the controlled current, that we now see the non-linear capacitance effect with a sort of hockey stick approach here. So slow at the beginning, at the bottom, and much faster at the top. And that's the non-linear capacitance, millicapacitance effect. By the way, on these we use the, just to check the load current was the right current. We get it, we're not overshooting or doing anything too horrible here. A bit of overshoot here, but we slowed it all down here, and you can see that happening there. moving on to the superjunction MOSFET. Again, really fast, 32,000. Oh, did I say that was that? That one's not 32,000. I think that was. Let me just check that. Sorry, that's a mistake. I think that's about 12,000 microseconds. Anyway, doesn't matter. It's still fast. The superjunction MOSFET is super. Was that 5? Oh yeah, the superjunction MOSFET is really, really fast again. But notice what happens here, that the gate drive is having to work very hard and the gate voltages are going slowly. If we slow down the gate current, really the gate's hardly doing anything. This is only, to be fair, this is only just about 1.5 microseconds across here. So it is very fast switching. Very fast DVDTs, very clean waveforms. But notice a bit of the EMI coming back in. So interestingly, the superjunction switching is very similar to the GaN in some ways, except you've got so much input capacitance to drive. So there's the IGBT, and everybody says IGBTs are slow. Well, they're really not. This is 0.2 microseconds. So again, about 0.2 microseconds per division, so about 1.5 microsecond pulse. Very clean switching. You can see this current tail in the switching. That's typical for an IGBT. You can see again, you've got a big Miller effect coming from this nonlinear capacitance down here. That's again typical IGBT switching. You know, I'd see, other than lack of overshoot, you could be looking at sort of 500 amp, 1000 volt switching waveforms here, except the time frame would be different as well. But the no overshoot here, very fast switching. It's pretty clean. Okay, moving on. Putting it all together, you can sort of see them side by side, and you can really see that this is very clean gate waveforms, very clean switching, doing very nicely. All the devices really are performing quite well. Interestingly, the silicon carbide MOSFET with so much capacitance to drive, it's very hard to get it into its on state cleanly around this corner. And in fact, the IGBT comes on pretty cleanly, pretty nicely. So it's quite interesting to do these comparisons if you're designing a particular product. So let's make some conclusions. Which is the best? Well, I think the GaN and silicon carbide, but particularly at these current levels and voltage levels, the GaN device is a great opportunity to get low conduction losses, low switching losses, and a really small footprint. And if we've got low losses, that means very small heat sinks, very easy cooling, and that makes life a lot better. And then, as I say, at these voltage levels, the silicon carbide MOSFET is losing out a little bit. We know that silicon carbide MOSFETs will go up to 10,000 volts even. So there's a place for them, but perhaps not at these levels. But low capacitances, particularly in the GaN device, low drive, lots of gain in the GaN. So these are pretty impressive, really. But don't, as we've seen there, don't forget the traditional silicon fight back and still offer a very impressive switching, even the IGBT. So it's a bit more, the IGBT is not your classic IGBT, it's a very fast one. And in fact, even there, we can benefit a lot from careful circuit design and get rid of all these overshoots and so on. And then we get the advantages of the better rating. Okay, the GaN devices, of course, silicon carbide devices, no tail currents and diode reverse recoveries and so on. So we really like those devices. So quite a lot of difficulty if you're testing building a circuit and trying to test it. Build in measurement if you can, because that's really going to help. And what's the verdict? Well, below 400 volt GaN is hard to beat. So we can take questions.
Alrighty, guys. Thank you very much for that great presentation. We, as always, as I see on this stuff, it just reminds you they should never take for granted the design technique and everything from, like you said, the instrumentation of, even the characterization portion to the layout and everything else to make the spec sheet stuff and promise of these wide bandgap things a reality. So thank you very much for outlining that so well. So we do have some questions right now. I want to remind everyone who's on that if you have a question, to please type it into the chat window. It doesn't matter if you send it to everyone or just to me, Brian Zonstecker, the host at the top. But right now we have 4 questions in there from 2 people. So the first one comes to us from Ian Mosley. Hopefully I'm pronouncing your name right, Ian. And first question is, what benefits over traditional devices do you see in using wide bandgap devices in resonant switch converters such as LLC and phase-shifted full bridge?
Oh, I think that's a really good question, which we're not addressing here because we did hard switching, but the on-state voltage is fantastic of these devices, and I did replace an IGBT with a silicon carbide MOSFET in an induction cooker, typical induction cooker hob, and the performance was fantastic. The device, of course, costs a lot more at this stage, but the losses are about half for the same package, same circuit, same everything. So resonance, I think, is a very interesting direction to go.
Alrighty.
Yeah.
So let's see, and we have a question from Dave, who's just Dave. What weight copper can be put on a flexible polyimide layer?
Okay. Hello, Dave. It's Edward here. So on the flexi circuits that we were working with, we specified 2-ounce copper. You could certainly plate that up and say maybe go to 4 ounce in total thickness. Really, it's up to the vendor, your PCB supplier, to see what they can get hold of. But certainly 2 ounce is readily available, and I expect higher ounce copper and plating up is a way to go if you want more current.
What have we in the wide bandgap one? What have we got?
So that's 4 ounce copper on that, and actually we have another circuit board that we've been working on for a slightly different application that has 6 ounce copper on it. So. Okay.
All right. Thank you, Ed. Next question, this one again comes from Ian, and he says, how do you arrange heat sinking around the devices when everything's so small? Any tips? And I'm assuming that's not a pun.
Okay, so Edward here. So yes, that is an issue because now you've got some concentrated heat sources in terms of your power devices close together. The pads on them potentially quite small. So I think that just comes down to having a very good thermal interface and potentially spreading it with some copper plates. And one thing to think about is that the devices don't necessarily have to be that close to one another if you have multiple devices in your circuit, because you're using a very low or very thin circuit board construction in order to minimize your magnetic fields. And therefore, if the devices are actually spread out a little bit, the impact upon your inductance, providing you get circuit design right, shouldn't be that great. So potentially you could have a bit of space between your power switching devices, and that should help with the thermal issues when it comes to putting them onto a heatsink.
Yeah. All right, and let's see, we're starting to get questions here for some other folks. We have Roberto Quintal Palomo, who asks if he has a 3 kW PM generator, maybe that's with BEMF around 400 volts. Can I use GaN active rectifiers? Obviously, the 400 volts is only when not loaded.
What does GaN go up to? I mean, I get the 600 volt.
650 volt.
650 volts.
So that sounds reasonable.
It sounds reasonable. I mean, that was part of the game is that we don't have to do a sort of 2-to-1 ratioing here. So I think the 650 volt. I mean, it's a challenge, but that's for sure. But it's a very worthwhile route to go down, I think, with 650 volt devices that are available. Yeah.
All right. Let's see. We have Julio De Donato, who says, can you comment on the use of a current viewing resistor instead of your current measuring circuit?
I'm not quite sure. He probably means a current resistive shunt.
Coaxial
The
shunt?
coaxial type, I think. Would that be right?
And
Yes,
Julia,
yes,
if you want to
yes. Okay,
clarify.
I see yeah.
Okay, yeah.
So it's Edward here. I'll comment on that. So I noticed that some people have used coaxial shunts with these sort of fast GaN circuits, and with sort of mixed results, really. I think one of the problems is that typically the coaxial shunts have quite high resistance, and you'll see from the circuits that we presented here that actually the resistive shunts that we're using are very low resistance, and therefore you get quite a low power dissipation, low voltage drop across the current sense resistor. And the second point is that in order to if you look at the geometry of the coaxial shunt, whilst you're inside the coaxial shunt part of it, you get magnetic field flux cancelling. The problem is when you come to the end. At the end, you sort of get a sort of fringe effect where your coaxial shunt no longer behaves like a low inductance current path, and therefore you have this sort of actually quite high inductance sort of end effect. And so instead of doing that, what we've elected to do is build the resistive shunt into our very flat, planar, low magnetic field current path on the PCB. And we found that to be a much lower inductance, much higher performance, better way of measuring the current.
Yeah, I want to jump in there too and just say that quite a lot of people have tried these shunts and they're just not getting very good waveforms. Now that may be for other reasons, but when I was working on gate turnoff thyristors many years ago, we reduced the resistance of the shunt because we were switching 3,000 amps, and we then compensated the shunt because as your resistance goes down, your inductance is staying pretty much the same. So you're getting more and more voltage off the inductance. So you need to start compensating it out. So I did have a paper on that many years ago. So it's just sort of backing up what Ed says. So we decided to go down just a straight resistor route, build it into the circuit, and compensate out with some success so far.
Alrighty. Stephanie is asking, for what type of applications would you recommend the use of these devices, and did you try them on a specific application?
That's a really good question. I have to say the permanent magnet generator application that Guilo mentioned. No, it wasn't Guilo. It was lost it now. One of the previous questioners asked. I think that's a really good potential sort of application because you end up with a high. If you put a lot of magnets in there and a lot of poles, you end up with a high frequency that you need. So sounds great to me. But we ourselves are working on a few applications that we can't talk about, I'm afraid to say.
Okay, it's Edward here. So I think Patrick's made some good points there. But on top of that, I would say, in general terms, anything that has is hard switching. Okay, so you can use it for resonant converters as well, but that's sort of a bit of a separate topic. But if you want to hard switch these devices, and so anything that is potentially mains connected, like a PFC front end, where you need a filter, really then GaN comes into its own because you can switch the devices very quickly. You can reduce the size of the filter components dramatically, so that actually then your the increase in the cost of your power devices is then more than offset by the decrease in the cost of the filter components that you need in order to meet grid codes. So anything really that's mains connected would be a good application for GaN devices. And there are many other applications as well that require high frequency switching.
Yep.
All right, our next question comes from Mehdi. And Mehdi asks, it was mentioned that the inductance of your PCBs are around hundreds of picohenries. That's great. But can you please clarify the accuracy of the measurement device?
Okay. Hello, Mehdi. So what we used for that was a vector network analyzer. All of the tests we have done, we build test fixtures in order to first calibrate the equipment, and then the tests are done in the test results that we showed you in this presentation really just a small subset of the total number of tests we've done. But there is a sort of procedure that you need to go through in order to validate the measurements you're taking as you go along. And that's really just a question of kind of figuring out for the particular set of tests that you're doing and validating it via different mechanisms so that you can be sure that the results you're getting are reasonable. And certainly you can see from the switching waveforms, which is the sort of final test in the sequence, that the voltage overshoots that we're getting, if you look at the DIDTs that we're measuring, then really that is ultimately demonstrating the low inductance commutation loop because there is no voltage overshoot present. But in getting to that point, there are a whole bunch of other tests on vector network analyzer, doing step response tests, most of which we obviously didn't have room to show here, but all those tests really go to give us confidence that what we've presented to you here is correct and valid.
All right, thank you. Next one, and my apologies ahead of time if I butcher your name, Mr. Arvanatopoulos. He'd like to know if it'd be possible to make a prediction if the 3C silicon carbide IGBT might be a better candidate comparing to a GaN hemp instead of the 4H silicon carbide.
I suppose. Yeah. Wow.
Just the moon, right?
I'm probably not the best person to answer on those sort of technology things, but I think everybody's gone down the route of the 4H. I think, haven't they? For the time being, there are interesting challenges with silicon carbide, and one of them is the sheer manufacturability and getting the the internal gate resistance is a bit of an issue. In fact, on that table I gave, is I think 18 ohms or something. On the one of the Wolfspeed devices, it's 5 ohms. So they're often driven with no gate resistor at all. And that's down to just how you manufacture the gate and what you can get away with. So I know I'm slightly avoiding the question, but because it's off my field, but bringing it round to something that is in my field, there's lots of challenges. Well, not lots, but there are challenges to making devices that we really want to use, and the channel mobility remains a challenge. And maybe trenching the channel and trying to get that surface lots of good research going on in those two areas really of gate connections and channel mobilities. And that's sort of, I don't know, everybody, you'd probably have to ask somebody else about the actual starting material. But.
All right. The next question, and this is a good one for you guys. We didn't make much mention of the fact that this is actually the second in a series of 3 PELS events kind of related to wide bandgap switching, particularly around the Google Little Box challenge. So this next question, I think, is a segue to that. Anthony Middleton asks, do you think it'd be beneficial to use a multi-level GaN approach compared to SiC for a high voltage, say 1,000-volt design?
Okay. Yeah, so it's Edward here. So this is an area that I've spent a bit of time researching on other projects, and the answer to that is yes. You can, if you get the circuitry right, you switch the devices fast, you can make some significant performance benefits, cost benefits by splitting a high voltage problem up into smaller levels. And really that comes from the devices, low voltage devices, switching faster, so they're more efficient in terms of switching losses. And also because your output waveform, instead of switching between the extremes of the positive and negative supplies, now actually PWM can be applied in a neutral point 3 level converter, now just between 0 volts and a negative, or if you have more levels, then that PWM voltage decreases further. And the upshot of that is that then your filter components become a lot smaller. The losses in those components become smaller. And so in terms of losses, going to multi-level, huge wins to be made. Of course, the downside is there is an increase in complexity, and that comes really down to design issues. So I agree with you that there are some significant benefits if you're prepared to put in the design effort to make a multi-level converter. And perhaps that should be the topic of another presentation, because I think there's a lot of interesting discussion and material that could be presented on that.
That's right. Very good loaded segue, Edward. Is we, of course, people probably don't know that you and I have been working together for probably about a year to try and put something like this together. So there's I know you guys have a lot more good stuff to talk about that we'll try and address in the future.
Okay.
We have a couple more questions here. Masi Kodabande asks, are ferrite beads still suitable to suppress EMI problems in GaN and SiC?
I'll take that one because I'm old enough to know that what ferrite beads do. You've got to put them in somewhere, and the way we've gone is to, really go, try and do everything with PCB and so on. But I think there could be a place maybe, but I'm not convinced at the moment that we should go sort of in that direction. What a ferrite bead does is it takes energy out of the ringing, and and that actually is a valid question in these circuits where you've got capacitance and inductance. But the key thing, of course, is you get the inductance down far enough, then you can take the energy out of the capacitance just by effectively losses in the device. You could see it that way. So it's I would not see it as. In fact, the best place I always used them in the past was actually on the gates, because you can get ringing and stuff. But hey ho.
So I think it's Edward here. In order to add the ferrite bead into the circuit, at least within the switching commutation loop gates, loops, etc. in the circuit, in order to add that ferrite bead in, you would need to in some way lift the current off the surface of the board through a wire, or perhaps you wrap the ferrite bead around a hole in the board. You could sort of integrate it in that way. But in any case, what you're going to do is dramatically increase the inductance of the circuit. And really what we're demonstrating here is that the best way to deal with ringing and the energy contained within that ringing is to have low inductance and then to clamp the voltages so that ringing is then, or any energy within that ringing is actually then returned to the power supplies, either the gate power supply or the main DC bus power supply. So dissipating it in ferrite B is probably not a route that we would talk about here. But then perhaps if you have a larger ferrite material and use it on the main power supply or the output, if the circuit is applicable for that, then maybe that's a valid place to put it.
Yeah, I think there is a point there, because we've used, if you like, parallel capacitances with the surface mount devices and the big blue ones, and that can cause issues actually with ringing between the two capacitors actually. So there are, I think, there's always a place for these things somewhere, just finding the right place.
But it's safe to say that in the circuitry we have here, we haven't used any ferrite beads, and we didn't feel that we needed to.
Yep. All right. Let's see. Chris asks, what kind of switching loss do you have associated with the overshoot current?
Yeah, it's the overshoot current is nothing you can do with about it, because it's from the capacitance of the device mostly. A little bit was from the layout and circuit board. We haven't done the loss calculations. We hope at some point to turn this into a academic paper where we do all these calculations. You can kind of figure out stuff from waveforms that are there. At one level, there's nothing you can do with it. That capacitance has to be charged up and discharged each cycle. So we just have to live with it. It's not something we've created.
And really the only way to get around that is to look at more complicated sort of pseudo resonance circuits where you actually use that capacitance to then slew the output voltage.
Yeah, absolutely.
But that's a level of sophistication beyond the hard switching that we're presenting here.
All right, and since we're on that topic, there's a related question here from Mehdi, who asks, how much of the current overshoot at the turn-on instant is due to the imperfection of sensing probes and circuits? So since the probes and sensing circuits have dynamic response, they may affect the waveforms shown on the scope. Can you please comment on this?
Yeah, you could tell that we've got some problems with the EMI, certainly on the switching of the GaN devices, because they're so very fast. So that has affected our quality of our current measurements on the wide bandgap development platform. But on our Ferrari, on our GaN development platform, we didn't have that problem. So we're a lot of work, a lot more man hours, I think it's fair to say, went into the GaN, trying to develop the Ferrari, than went into the wide bandgap one. And the wide bandgap one was also to be more practical in a sense.
So we relaxed some of the constraints on the design of the wide bandgap development platform. And one of the consequences of that was that at the very, very high switching edge rates that you see on the GaN devices, clearly there's some EMI getting back into the current measurement circuit. On the GaN development platform, we had much closer ground planes. Everything was much smaller in terms of the layout, much smaller components, and therefore that pickup, even at very high slew rates, wasn't a problem. And in fact didn't appear at the output of the current measurements as it went to the scope. But I think one of the things you can clearly see from the calculations that we did the end of the GaN development platform section. I'll just roll the presentation back for that. I think this is a
Yeah.
Very valid point. So we asked the same question. Well, are the waveforms that we were getting realistic? And so, you can look at that current spike and you can ask the question, where is that coming from? Is it some sort of reverse recovery issue with the top device? Well, we know with GaN that is never an issue due to the construction of them. So then we perform this calculation here on the spike as it appears on the oscilloscope, looked at the area under that spike, and that gives us the charge in coulombs, and then compared that with a theoretical calculation on the capacitance of the device, the strain inductance that we measured on the circuit board with the vector network analyzer. And you can see here that the two calculations give very closely the same answer, and therefore, given all of the tests that we've done to achieve confidence in our measurement and given this calculation, I think it's fair to say that we understand where that current spike is coming from. As Patrick said, it is an inevitability of the powered devices. It is inherent within their structure, so there's nothing we can do about it. I think that normally people don't see it because you get a lot of ringing on the measurement circuits when people are normally switching these devices, and therefore that ringing masks that initial pulse. But here, with such clear, accurate measurements, you can see it very distinctly. So,
yeah, I'll take over there as well. In that the people have been concerned about this effect because of the thinner device with the wide band gap. You get more capacitance. So you cut the area of the device down, but you still got that much thinner depletion layer and structure, which gives you quite a lot of capacitance. So academics have been worried about that. Actually, going back to the measurement thing, I don't know if I could find the slide real quick, but if you look at some of the slower switching waveforms of the current measurements, you can see that they're very clean, and the timing is right, the features are right. So, I think we're pretty confident. Yeah, slide 42, but I don't know the number.
Roll to that one.
Yeah, that's good. Yeah, you can see that you've got. Here you've got the volts rising fast. You've got a little cut in current, and then the current drops down. Okay, it sort of undershoots and does something a little bit strange here. Coming up, we're switching slowly. You've got a non-linear. We've got a constant current gate drive, so your gain, your GM, is increasing. So the current comes up faster as you come up there. These are what you could call textbook waveforms, other than this little bit of stuff here. So then when you come over to the faster switching, you then say, oh, well, okay, you've got something going on here, and there's a lot of ringing and stuff, but there's definitely something in there. So I think, we've pushed our current measurement system to its limits, really. I mean, to be fair, this is still 100 nanoseconds current rise time across here, and it's as clean as a whistle. So it's tough, and we acknowledge that it needs improvement.
Yeah.
All right. Let's see. I think we get a couple more quick questions here. Dave asked, when using GaN transistors for a DC-DC converter, would you recommend using 2 transistors or 1 transistor and a diode?
So I think, if you're not going to hard switch it, you're not going to switch the top device, then I would use a silicon carbide diode there. You need to use something that doesn't have any significant reverse recovery associated with it. We've only used the GaN device as an upper catch diode in these experiments because we wanted to simulate the effects of hard switching in a converter circuit. But if you don't need to do that, then there will be no sense in having the top GaN device, because that you are going to incur quite a high reverse voltage drop across or through that top device when it's acting as a diode. Again, that is an inherent sort of feature of the GaN power switches. But of course, in a hard switch converter, you would then, once the dead time is over, you would then immediately switch that upper device on, in which case your voltage drop and your power loss through that top device then diminishes quickly.
Yeah, it's quite a complicated answer, but it's absolutely right. Yeah, I was checking. It's absolutely right. So the silicon, the Schottky diodes are just fantastic. So if you can use them, then that's great. But if you need to switch effectively synchronous rectification type of thing on a full bridge leg is fine if you need it.
Yeah.
And it's great. That's another advantage with a MOSFET device, of course, is that you can reverse conduct the channel and use it as a synchronous rectifier or freewheel diode. And the very short period of wide bandgap, high voltage diode, well, 3 volts or something diode is so short it doesn't matter in the run of things. So it's really on your application.
Yeah, very good question.
Really, yeah, absolutely.
All right. Well, there's one more comment here. Someone's feeling your pain, and then I think we'll take a last question. So Ian Mosley says, we've seen the capacitor turn on current pulses on our wideband gap measurements, too. They can be a big problem with hard switching at high frequency. So it's a little empathy for you guys. And we're going to close it out with a question from Mr. Arvanatopoulos. I hope I'm getting better at that. At the comparison of the technology switching characteristics, GaN, SiC, and silicon, is there any information on the active area of the DUTs? Are they all of similar active area?
Yeah, that's a good question.
So no, not similar active area, but what we tried to do in the four-way showdown was to pick devices that in a typical application could be sort of substituted between one another. So we went for sort of similar on-state resistance, RDS on. And for the IGBT, what we did was sort of calculate an equivalent RDS on its on-state for sort of an equivalent loss.
Yeah.
All right. Well, I think we're going to wrap on it there. Once again, I'd like to thank Edward and Patrick for your great webinar today, and especially for hanging on, a full 30+ minutes extra to handle Q&A. I'd say the audience will applaud you, but since they're all on mute, you can assume there is a wild applause and standing ovations that you are unable to observe. And thank you very much for being part of this. I'll remind everyone again, this full webinar, including the Q&A up to this moment, will be has been recorded and will be posted on the PELS website, which is where you should have gone to perhaps sign up, or you should find that link somewhere. You're welcome to email me, Brian Zonstecker. My email is bz@powerrocks.com, POWERROX, for any questions, concerns, complaints, and whatnot. And with that, I think we will call it a wrap. So thank you very much again, and keep an ear out for a lot more events coming out of the local PELS chapter here. If you are local in the Bay Area or plan to be 2 weeks from today, on July 13th, our next talk will be related on extreme power density converters, particularly switch capacitor, a new class of hybrid switch capacitor power converters from Professor Robert Palala of University of Illinois, Urbana-Champaign. So if you're in town, please register and attend that. It'll be a great talk. And other than that, everyone have a good one. Good day, good night, great weekend, and all that good stuff. Thank you very much.